Let's take a closer look at braking in MotoGP, what types there are, and how much control the rider has. First of all, there are 3 types of braking force that every bike has. The front and rear brake, which are controlled by the riders, and then the engine brake as well. As we can see, the front brake takes on the majority of the workload with 70% total braking force. The engine brake accounts for 20%, and the rear brake, meanwhile, only accounts for 10%. The front brakes are 100% rider controlled and features 2 carbon brake discs and brake pads, important when stopping from over 320 kilometers an hour. The engine brake is controlled by the wheel and the electronics, meaning it's variable per corner. It doesn't have any rider input, and it's all down to bike and ECU. Finally, the rear brake. It only accounts for 10% of stopping power, meaning a steel disc is suitable. It's 100% rider controlled, and riders can either use a lever on the right foot or a lever on the left handlebar. In the end, it all comes down to personal preference.
Typically, when approaching the corners, riders have two options. They can choose speed and try to outrun their competition, but risk sacrificing accuracy and control, or they can rely on the brakes and corner as tightly as possible, but lose speed. As we can see, the Movistar Yamaha bike is cornering at high speed, using progressive turning. Releasing the brakes early carries much more speed through the apex, but having a much wider angle through the corner, whilst the smooth throttle on exit helps to maintain a good speed. The Repsol Honda bike here, meanwhile, squares off, relying much more on brakes and acceleration of the bike. The rider releases the brakes later and accelerates hard out to the apex. The Movistar Yamaha rider takes a much wider racing line, going faster through the apex, giving him more time to lean and needing much less grip. The Repsol Honda rider, on the other hand, uses the fat part of the tyre, needing more grip for the tighter angle and timing the lead more precisely. Both types of cornering have their moments, and while some riders and bikes favour a certain style, a rounded rider will be adept at both. Let's take a look at downforce and top speed in MotoGP and some of the trade-offs that must be made when deciding whether to ride with or without the aerodynamic fairings. Top speed can only be achieved when the riders open up the throttle. Depending on whether they're riding with the fairing depends just how fast top speed is. The standard fairing allows for a higher top speed and greater agility. This has to be weighed up against reduced stability when braking. The aerodynamic fairing, on the other hand, provides more downforce, reducing the wheelie and increasing the front tyre contact whilst improving stability when braking. The shape of the fairing can have a significant impact on the drag, which can be used to the rider's advantage. The standard fairing creates less drag and creates less downforce, which could lead to more wheelie when accelerating. The aerodynamic fairing, on the other hand, creates more drag but directs it to keep the front tyre on the track. Ultimately, it's the aerodynamic fairing that keeps the wheels in contact with the asphalt for greater acceleration, whereas the standard fairing allows the rider to reach a greater top speed. Let's take a look at what the steering damper is and what it does on a MotoGP bike. The bikes in MotoGP have a short wheelbase and aggressive steering geometry, which is great to help the riders change direction quickly, but can cause instability, uncontrolled movement and wobble when accelerating. The steering damper is connected to the handlebars and the front fork and stabilizes the steering, preventing uncontrolled movement. The damper can be adjusted to suit the rider's feeling, giving them more or less damping, making the bike more or less reactive to sharp steering movements. With less damping, the bike steers more freely. The rider gets more feedback from the bike, but that can also be a downside as the stability decreases. When accelerating, the rider has much less control of the bike, which could lead to wobble with serious consequences. With more damping, the rider has to work more to steer through the corner, but gets much less feedback. More damping does, however, provide more control and reduces the risk of wobble when accelerating. Tracking of a MotoGP bike, how it works and what it can do. GPS positioning is not allowed in MotoGP, but there are other ways for the bike to identify its location on a track. Using onboard sensors, the bike can measure how far it's travelled. The sensors then transmit information to the ECU, which is reprogrammed for each race and each track, and so can use the data to reset at different points and different sectors on the circuit. The bike location can be used for corner-by-corner electronics, where the ECU will deliver settings best suited to the corner that the bike is on, controlling things like engine torque, traction control, engine braking and anti-wheelie. These adjustments in the electronics can greatly help the riders to get the most out of the bike at each point of the race, especially when decisions need to be made in hundredths of a second. Take a look at oversteer and understeer in MotoGP. What is it, what's the difference and what does it do? Understeering and oversteering are ways of manipulating the bike throughout a turn. Riders can adjust their steer angle, oversteering or understeering to compensate for speed or to line their bike up for the next section of the circuit. Understeer is when the side slip of the tyre is greater than the rear, pushing it away from the turn. Here the front tyre has significantly less grip than the rear tyre. The problem with understeer is the risk of running wide as it's hard to turn and correct. Sliding the front wheel increases the wear on the tyre and the rider could risk crashing. Oversteer is the opposite and is much safer, when the rear tyre slides out away from the radius of the turn more than the front wheel. The front tyre maintains much more contact with the asphalt than the back. Oversteering can help the rider with turning, keeping them tight into the turn and straightening out from the apex faster using the throttle and electronics. The bike's traction control can help riders recover their control of the bike and avoid crashing. Let's take a look at the front springs of the MotoGP bike, how YGs might change them and what the effects can be. Common suspension rates in MotoGP go from 8.5 newtons per millimeter being the softest up to 10.5 newtons per millimeter on the harder end. MotoGP riders may choose to have a combination of spring stiffnesses in their front forks. The stiffness of the springs is crucial because if the front shocks are too soft, the bike risks dropping too far forward when the riders hit the brakes. On the other hand, if the springs are too hard, the pressure from braking gets transferred onto the front tyre and causes a lot of wear very quickly. The front fork is assembled as a single unit and the two springs work in unison. The teams can change the springs really fast, typically taking less than 2 minutes. Riders can choose to combine springs in the front fork to achieve a more precise overall stiffness. That's how riders choose their suspension stiffness in that front fork. The exhaust systems on a MotoGP bike, how they can be modified and what the results of those changes can be. The exhausts have two main purposes. Firstly, to remove the waste gases from the engine and also to draw air and fuel into the cylinder for burning. Believe it or not, but the exhaust can have quite a profound impact on the performance of the bike. It can increase the power within rev ranges. As a result, this can change the throttle feel for the rider, making the throttle more or less smooth or sensitive. The length, width and even the shape of the exhaust can be modified, affecting the flow of air and gases to and from the engine, allowing more or less exhaust fumes to escape faster or slower and increase or decrease the back pressure and upstream. The exhausts are made from a titanium alloy that's extremely heat resistant. This is important because at high speed, exhaust gases can reach 1,000 degrees Celsius. MotoGP teams are allowed to change their exhaust throughout the season and so can use this to adapt the bike from circuit to circuit. Wheel spin in MotoGP. The rear wheel is what drives the bike, giving it acceleration and propels it forwards. There needs to be a speed differential between the front and rear wheel, so the front wheel spins slower than the rear wheel, or the rear wheel spins faster than the front wheel, whichever way you want to look at it. This is why we get that forward push. If they were both going the same speed, we wouldn't be pushing that front wheel. As a result, the speed of the front wheel is the true speed that the bike is going. Specifically with slick tyres, to get that forward thrust, the rear wheel needs to spin around 8 to 12% faster than the front wheel, depending whether we're on a straight, accelerating or cornering. Also the grip level and the tyre softness. Let's take a look at an example. If the bike is travelling at 330 km per hour, the front wheel spins accordingly. The rear wheel, however, is spinning 12% faster at 369.6 km an hour, so we get that forward thrust that we've been talking about. And that's rear wheel spin in MotoGP. Parts on a MotoGP bike, and around 200 of them, need changing at various intervals due to wear and tear. Let's take a look at some of the more important ones. Over an average race weekend, from FP1 to the end of the race, a rider can put in around 500 kilometers on their bike. Over this period, the teams have to change the oil, water and chain. Every 1,000 kilometers, the teams have to replace the sprockets, clutch plates and the carbon brake discs and pads. Every 1,200 kilometers, the teams must completely replace the wheels. Every 2,000 kilometers, or around 4 races, teams must completely remove and replace the engine. Every 4,000 kilometers, or around 8 races, just under half a GP season, teams have to replace the handlebars and seats. After around 9 races, half a GP season, the teams replace the bike's frame and swing arm. That's parts mileage in MotoGP. As much grip as possible, whilst preventing oversteer and high-siding. The inertial platform in the IMU detects the lean angle, while sensors in the wheels detect the amount of wheel spin, indicating how much grip the tyres have and how much contact there is with the track. If the rear wheel loses traction, meaning the grip drops and the wheel starts spinning faster than the front one, the back wheel can swing out wide, causing oversteer. Should this happen, the sensors talk to the ECU, which cuts the power by cutting one of the cylinders, closing electronic throttle, or reducing the ignition timing. This is important because if the bike were to suddenly regain grip, it could high side, causing a crash and potentially injuring the rider. The teams can tailor the traction control to each rider and bike, as well as customizing it for every turn. As the grip decreases due to tyre wear, the speed or the nature of the corner, the traction control increases the traction to maintain contact with the track. And that is traction control in MotoGP. Chiang International Circuit in Thailand for the very first time. Racing at a new track can be difficult for the teams to set up the bike. What we do know though is that in Thailand it's hot and humid. The teams can therefore increase the size of the carbon brake discs to 340mm, allowing them to keep cooler. If the rider already uses a 340mm discs, then teams can add airflow intakes to direct the air to the brakes and keep them cool. The grip level is a big question mark for the Chiang International Circuit, so the teams will be trying out different suspension hardnesses to improve the grip, switch off the springs, create more grip by transferring more of the bike and rider's weight onto the tyres. This can, of course, affect the wear of the tyres. For the long straights out of turns 1 and 2, as well as the tighter parts of the circuit, the teams might play with the length of the bike's wheelbase and height. Lengthening the wheelbase and lowering the height can affect how much the bike wheelies when accelerating away, but can affect the turning stability. Let's see this weekend how the teams set up the bikes for the PTT Thailand Grand Prix. As each track is a different length, the teams must carefully calculate how much fuel is used over a race distance. The amount of fuel that a bike uses can be electronically adjusted to fit the circuit, but the teams must use all 22 litres for maximum power, without, of course, running out before the finish line. Naturally, temperature affects the volume of the fuel, with the volume increasing in hotter climates and decreasing in colder ones. As a result, fuel is measured in weight by kilograms rather than by litre. For example, a full 22-litre tank will hold 16.5 kilograms of fuel at 15 degrees Celsius. At 25 degrees, the same weight of fuel would cause the tank to overflow, whereas at 5 degrees, the tank would be only 3/4 full. So the teams have to adjust the amount they use based on ambient temperature. Teams are allowed to cool the fuel by up to 15 degrees below ambient temperature before the race to fit more in the tank, which leads to more power. The rider leans into a turn to create a centrifugal force, forcing the bike through the turn and counteracting the centrifugal force, which pulls the bike and rider outwards. The rider starts the turn by counter-steering. Contrary to what you might expect, the rider actually steers in the opposite direction of the turn, causing the bike to lean into the corner. If the rider didn't do this and turn the handlebars into the turn without leaning at such high speed, they'd be thrown outwards due to the centrifugal force, like a high side and undoubtedly crashing. Once committed to the turn, the rider continues through it, leaning, often using their knee and even elbow for stability, and begins to steer into the turn. The amount that the rider will lean depends on how tight the corner is, how fast they are going, and the grip levels of the tyre and surface. And that is leaning and cornering in MotoGP. Trail braking is a technique that riders use as they approach the turn, applying the front brake to reduce speed and slowly letting off the brake as they lean through and exit the turn. MotoGP tyre is specially designed to give the rider's grip at a 64-degree lean, despite the contact patch with the asphalt being around the size of a credit card. The bike's carbon brakes, meanwhile, are designed for consistent brake level feel from the start of the race until the checkered flag has fallen. Preparing to enter the corner while still upright, the rider will release the throttle and squeeze the brake. As he enters into the corner, he'll counter-steer and lean into it. He'll maintain the force on the brake lever throughout. As long as the grip is good, he'll hold onto the brake for as long as possible as he approaches the apex before releasing the brake and opening up the throttle to accelerate away. And that is trail braking in MotoGP. Fundamental ways of preventing the bike from wheeling, looking at the electronics, the fairing and the rear brake. Starting with the electronics or ECU on the bike, sensors detect when the bike is beginning to wheelie and send information to the ECU. The ECU then talks with the engine, briefly cutting the power and then letting it increase again as the front wheel lowers back down. Now, with the fairing, teams use an aero package which, like a spoiler on a car, directs the air upwards, therefore pushing the bike down, almost the opposite of the wings on an aeroplane. The faster the bike is going, the more downforce is created. And finally, with the rear brake, the riders can apply the rear brake via the foot pedal when accelerating, slowing the bike down slightly so that the front wheel lowers back down. Teams and riders can mix and match these methods as needed, and that is anti-wheelie in MotoGP.